Hi everyone, this is Mrs. Bustamante. In this video, we're going to talk about 7.5, which is about Hardy-Weinberg equilibrium. And before we start, we're talking about equilibrium. If you think about just the word equilibrium, we're talking about equal or balanced, right? So it's really going to be a way for us to evaluate a population that is equal or balanced or not evolving in other ways. This first part is just to give you a little bit of background. Where does it come from? Well, it comes from Hardy and Weinberg, who actually independently kind of were describing the principle of basic population genetics, which is now named the Hardy-Weinberg equation, or equations actually, right? The equation is an expression of the principle known as the Hardy-Weinberg equilibrium, which states the amount of genetic variation in one population will remain constant from one generation to the next in the absence of disturbing factors. So what are those disturbing factors? Well, those disturbing factors are those 5 things we talked about causing allele change in a population. So when we think about the Hardy-Weinberg equilibrium, newsflash here, it's actually pretty impossible, right? I don't know of a population we have yet that doesn't follow any one of those rules, right? All 5 of those have to be not true, and we'll talk about how we state them here in order for a population to not be evolving. So really, Hardy-Weinberg is something kind of unrealistic for us to see in real life. But what does it do? It's going to look at alleles as indicators, right? So we're going to have, when we have organism, we're looking at a eukaryotic organism, we're going to think we have 2 chromosomes, right? One from genetic mom, one from genetic dad. They have alleles on them. We're going to talk about Mendelian genetics, so we're going to say alleles are either dominant or recessive. And you have one allele on chromosome 1, another allele on the homologous chromosome that code for the same type of gene, right? So we have 2 alleles that code for the same phenotype. And we're going to assume basic Mendelian genetics most of the time. So when we look at alleles, we can use them as indicators of the evolving population. If they're changing, right, if the frequency of them is changing, we're going to see that population evolving. If it's staying the same, it's not evolving. Oh, sorry. So what are those things? Well, we just talked about things that cause change, right? Mutation, gene flow, non-random mating, small population size, genetic drift, and selection all cause changes. So when we look at Hardy-Weinberg equilibrium, it's kind of like our null hypothesis. It serves as an example of if a population is not evolving. So we have to remove all of those agents of change that we just talked about. And excuse me, we have to say we have a large population, so it's less likely to have genetic drift. We have to have random mating, meaning there's no sexual selection and you're less likely to inbreed in a population. We have to have no mutations that ever happen, right? No chemical change to your DNA. We know these are rare, right? But to have none ever is pretty unlikely. We have to have no gene flow, meaning nothing is coming in or out of a population. There's no changes in it. And there's no selection of any kind. There's no natural selection, artificial selection, or sexual selection. Again, these all have to be true in order for to have a Hardy-Weinberg equilibrium population. Is that very likely? No, right? It's not very likely that all 5 of these things are true in order to see a population in equilibrium or not evolving, which kind of leads us to the idea that yes, evolution is happening. So again, Hardy-Weinberg equilibrium is your null hypothesis. It implies that evolution implies that changes in allele frequencies are happening. So if no evolution is occurring, what would you expect allele frequency to look like? Well, you'd expect that allele frequency would stay the same over time, right? If we know that changes in allele frequency imply evolution, if there's no evolution, you'd expect those allele frequencies to remain the same over time. So if no evolution is occurring, what characteristics would a population have in regards to size, mating, mutation, migration, and natural selection? Go ahead and pause the video for a second. Give yourself a moment to think about what your answers to those would be before I give them to you. So here's what a population would have to look like if no evolution is happening. Has to be large, right? No genetic drift. Has to have totally random mating. Has to have no mutations that happen. Has to have no genetic drift and no natural selection or selection of any kind in order to be in equilibrium or be unchanging. And again, we said that's actually not super likely. Okay, so Hardy-Weinberg is equations. They come up with equations to compare allele frequencies in a population, basically to mathematically look at how those populations of alleles are present. How present are they? How much of them are recessive alleles versus dominant alleles? If those 5 conditions we just talked about are met, then the following equations would apply. And the equation uses single loci gene traits of a diploid organism. So diploid organism, we have 2 copies of each chromosome. There's a gene at each loci. Each loci or each gene will code for the same type of gene, Each allele, an allele at each gene will code for the same type of gene. So 2 copies of each. All of these things we are assuming in the Hardy-Weinberg equations. So here are the Hardy-Weinberg equations. Now's a good time maybe to just pause it, write it down so you have all this written down and we can really think about what's happening here. I'll give you a second to do that. So we're back. Our first equation is allele frequency. So the frequency, how much of each type of allele we have, how much dominant allele we have, and how much recessive allele we have. So we can think of the entire population as being equal to one whole, if you will, and we're going to have part of it that is our dominant alleles and part of it that is our recessive alleles, okay? We let P equal our dominant allele frequency and Q equal our recessive allele frequency. And when we talk about things in frequency, we're going to talk about them as decimals, right? How do you remember P is dominant, Q is recessive? I just remember P comes before Q, so D comes before R, P is dominant. However you like, though, will work for you. They will give you the equations on the AP test, but you have to know what they mean, right? So what does this mean? If I have 0.5 of my population that is the dominant allele and 0.5 is recessive allele, 0.5 plus 0.5 equals 1. Okay, that would make up my entire population. I could also think about it, 0.3 was dominant. That would mean that 0.7 was made up of the recessive allele, again equals 1. Parts are equaling the whole. My next equation has to do with genotype frequency, and I'm actually going to change the page here, although it has all the same information on it. Okay. Genotype frequency is telling us what genotypes are present and then how much of the population is made up of that genotype, right? So when we think about this, I like to think about it from a dihybrid cross, right? We have a genetic mother, say, that is heterozygous, genetic father that is heterozygous, and we cross them. What are the possible outcomes of genotypes that we can get? Why do I do heterozygous? Because that gives me all the possible genotypes, right? Okay. First possibility we could have is a homozygous genotype. That would be a dominant A and a dominant A, for example, right? So A and A or P squared. Remember back when we were in genetics and we did probability, right? If we were, say, flipping a coin to determine genotype, 1/2 chance of getting heads and a 1/2 chance of getting heads at the same time, 1/2 times 1/2, 4. So that's just saying how much of your population is homozygous dominant. So P times P. They have both frequencies of those alleles, right? That's how we're gonna mathematically figure it out too. Flip side, we could also have homozygous recessive, right? Which would be tail, 2 tails at the same time. So Q times 2. We could say that's like 1/2 times 1/2 would be a 1/4, right? But there's one other part, the part in the middle, okay? We could also have a heterozygous genotype. And that would mean that you get a dominant allele and a recessive allele, right? And why do we have the 2 in front? Well, there's 2 different ways to get it. You could either have your mother give you dominant and your father give you recessive, or you could have the genetic father give you dominant and the genetic mother, say, give you recessive, right? So because there's 2 different ways to be heterozygous, depending on which order they come in, essentially we do 2 times the frequency of P times the frequency of Q. So these take into account all the different genotypes we could have in our population. And so if we take all the homozygous genotypes, all the heterozygous genotypes, and all the homozygous recessive genotypes, add them together, that's going to include our entire population, which is equal to 1. Okay, those are the Hardy-Weinberg equations. In our next video, we're going to talk about using them. What's a problem going to look like that you would see, and how would you use it, which I think for me always really helps it make sense. So make sure you have these equations down, make sure you know what P and Q means, and in a second we'll use them. Hope that was helpful. See you again soon.